Hi, my name is Ayan and today I am going to show you a cool visualization of electric field using Python. Let's say we have a point charge whose magnitude is Q and we want to calculate the electric field at another point P at distance R. The formula for electric field is given by this formula. This is probably, you already know, it is basically something we derive from Coulomb's law. Okay, now let me introduce you to the setup that I'm going to use today. So we will be having a bunch of positive and negative charges in the space, and let's say there's a point P where I want to calculate the electric field. I use the previous formula to calculate the electric field at point P due to all the charges and add them vectorially. Finally, I draw an arrow whose length is proportional to the electric field, and I repeat this process in the entire space. I divide the space into a grid of 40 by 40, and at each point I draw the electric field. So this is the code that I have written for my project. Let me run this code. So when I click on this positive, my code creates a positive charge at the center. As you can see, there are 1600 40 by 40 grid points in this space, and my code calculates the electric field at each point and draws an arrow which is proportional to the strength of the electric field. As you can see, near the electric charge, the arrows are longer, but as we move away from the charge, the arrows get shorter and shorter and shorter. I can grab this positive charge and move around, and at every instance the electric field at every point is redrawn. So it gives you a very nice little transitioning effect. Let's see what happens if we keep on adding a bunch of positive charges and arrange them. So as you can see, exactly in the middle of these two charges, the electric field is 0. We can arrange them in regular shapes. For example, it's a cube. Look at the electric field. It's very helpful. I mean, you can play around with this. I can play around with this animation, and I can visualize electric field all day. It's aesthetically beautiful. Now I'm going to show you the electric field due to dipole, something that we learn in college. So a dipole is basically a combination of a positive and negative charge. So as you can see, I have both positive and negative charge, and look at this. Look how smooth this electric field lines are. Look how cool is that. We can actually see another interesting thing called capacitor. So for capacitor, a capacitor is basically a plate, two parallel plates, where at one side you have positive charge, and on the other plate you have negative charge. So what I'm going to do, I'm going to put some positive charges, and I'm going to align them in a single plate kind of system, and then I'm going to bring another bunch of negative charges and I'm going to put them. Let's see what happens. Positive. Let me bring some negative charges as well. Yeah, let's put them. As you can see, as I'm bringing more and more charges, the electric field between these two lines are getting parallel, almost as if like perfectly parallel, and outside it's more of like a dipole. So yeah, you see, inside it's perfectly symmetrical and so beautiful aligned, right? Now I'm going to do something illegal. I'm going to introduce motion into the system. So I have 4 negative charges which are stationary, and there are 2 positive charges which are movable. The moment I click on the play button, they start to move. By the way, this is totally unacceptable and illegal to do. Why? Because we are having a system where we know both the position and the velocity of a charge, which is totally not allowed by quantum mechanics. And how I'm introducing it, I'm combining classical mechanics, which is Newton's law, and applying it to Coulomb's law. By the way, this should not this is not an accurate representation of moving charges at all. We can never have a representation, but why not? I'm just having some fun here. So thank you for watching. In the second part of this video, I will be discussing Gauss's law, and I will be exploring the idea that whether we can apply it in a two-dimensional world. Thank you for watching.